Okay. Okay. Hi. Good afternoon, everyone. Thank you for joining this webinar today. As Mas said, my name is Denise Ferreira, and I will demonstrate today a pushover analysis of a small Masonry house. Also, as Mas said, questions are welcome, so you can send your questions during the presentation, and I will try to answer at the end. You can also send an email afterwards. So let's start with a brief introduction about seismic analysis and a comparison between pushover and full nonlinear time history analysis. So both methods are used. Okay. Both methods are used for assessment of seismic safety, and they both account for nonlinear geometry and material response, and then can be also used for damage identification. So in the nonlinear model pushover analysis, we have a static nonlinear analysis where there's no damping or no cyclic behavior considered. So the lateral force is equivalent to the modal distribution, and this is automatically computed in DYANA. So DYANA calculates this lateral force based on the mode shape. In the case of the full nonlinear time history analysis, it is a transient dynamic analysis where we solve the equation of motion, and damping and cyclic behavior are accounted. So we input the acceleration history with time that can be in the three directions to reproduce the ground motion. So we can continue this comparison in terms of the pros and cons of the two models. For the main advantages of the nonlinear model pushover analysis is the simplicity, and that's why it is spreadly used. It is faster and easier to compare, and it is a well-established procedure. That is why it is considered in guidelines and codes for the prediction of the structural capacity under seismic loading. However, the disadvantages are that only one mode shape is studied at a time. So when we have symmetric tall structures that we know that which is the dominant mode, no problem. But if we have complex and non-symmetric low structures, this dominant mode might not be clear. So we need to study different mode shapes in different directions. Also, this dominant mode can change due to damage, and this is not accounted in the pushover. On the other hand, the full nonlinear time history analysis provides an accurate structural assessment, also accounts for the correlation between modes. It is indeed a realistic prediction of the development of the structural response, so the development of damage, displacements, cracks with time. However, it is a very complex analysis at a high computational cost, so we only can study a limited number of signals for the probabilistic analysis. So with this, I introduced the example that I'm going to model. It is a small house, 5.2 meters length, 3.2 meters width, 3 meters high. It has a foundation on grade, masonry walls, and a timber roof. So I'm going to demonstrate a pushover analysis until failure to determine the resistance of this house. And at the end, I will also like to show the results of a full nonlinear time history analysis and compare with the pushover analysis. Also, one thing I want to highlight is the near collapsed output tool that is available in DYANA It's a tool that retrieves the results for the step immediately before divergency, even if it does not correspond to any of the steps initially asked for output. And this can be great advantage for analyses that have a large number of load or time steps. So before starting the model, I just want to briefly introduce the material models that we are going to use. So for the concrete for the foundation, we use a linear elastic isotropic model. For the roof beams, a linear isotropic model. For the roof plate, a linear elastic orthotropic, where we change the shear modulus, varying the shear modulus. And for the soil, we don't model the soil itself, but we take into account the subgrade reaction as an interface. And for the masonry walls, we use the new engineering masonry model developed in DYANA. It is an orthotropic material. So first we input the orthotropic elasticity parameters, and then we choose a joint failure type. In this case, we will choose the diagonal staircase cracks. There are various options for joint failure in this model in DYANA, so please see the documentation for more information. So with this, I can start the live demo of this model. So I'm going to open the DYANA IE. Okay, and we start a new project. We will call it Masonry House. It is a structural problem and 3D. Okay. We check the units first. We will use SI units. And we only change the angle from radian to degrees. Okay. So we start the geometry definition by making the lines of the walls and extrude them. I will define separately the walls in X direction and Y direction. I will need this because of the orthotropic parameters of the masonry model. I will come back to this later. So I will start by creating the lines for the walls. So let's start with wall 1 in X. Okay. And wall 2 in X. Okay, and now we do the walls in Y, the lines for the walls. I can use the mouse here, so this is wall 1, okay, and wall 2Y, also use the mouse, okay. Okay, so now we extrude these lines 3 meters in the Z direction to make the walls. So we extrude. Okay, 3 meters so we can see. Okay. Next thing to do is a rectangular sheet for the door gap. So I will make this sheet and subtract it from this wall. So first I do the sheet. I have, we can keep this name, and I will get the coordinates from Excel. So I paste it here. You can see here the door, okay, and now we subtract it from the wall. So this is the wall. I can select from here, also select, not selecting the tool. Sorry, okay. and we subtract. We can preview this gap. Okay, it is okay. You can see here the shapes in the geometry browser. So we continue by creating the 9 beams of the roof, and I will add a straight line and then copy it 8 times with the same distance of 0.6 meters. So I first do the first beam, beam 1. Okay, you can see it here, okay, and also appearing here in the shapes. Now I copy this beam, you can select it from here, and I want to, the displacement is 0.6 meters in the y direction, you can see here the referential, and 8 times. You can see the beams, okay. Okay. So now we do the sheet of the roof. The roof slab is connected to the beams and not to the walls. So there is a 5 centimeter gap between the roof sheet and the walls in all the perimeter. So we do that, create a sheet, we call it roof plate. And I also copy the coordinates from Excel, put it here, okay. Okay. Finally, we make the ring beam for the foundation, and for that we create 2 rectangular sheets corresponding to the outer and inner perimeter. So let's start with the outer perimeter. I call it foundation to the sheet, foundation. So here is, I also copied the coordinates from Excel, here, okay. You can see it here, okay. And now we make the other one, the inner part. So we call it foundation out because we are going to subtract it. Okay, the coordinates from Excel, and you can see here this part. Okay, so now we subtract one sheet from the other in the subtract. Okay, so I want to subtract, this is the target and the tool is the foundation out. I can select from here and subtract, and I can preview, and we have our ring beam, okay, for the foundation. So the geometry of the house is completed, and we continue the model by giving the properties of the soil interface. So the boundary interface at the bottom face of the foundation sheet to represent the soil interaction, the contact between the foundation and the soil. So we do this by connection property assignment. We can call it interface. And it is a boundary interface because we are in the same dialog. In DYANA, you can put the supports in this interface at the bottom of the foundation. So we choose this, it is a face, and we select the bottom of the foundation. And it is structural interfaces. We need a new material. We will call it friction. It's interface elements, and we will use Coulomb friction. Okay, we add the properties. The linear properties and now the Coulomb friction properties. So we are here, here. Okay. Okay, and it's all. Okay, close. We also need, we don't need the geometry, we don't need data, we need to define the supports. We can call it base, support set base, and we fix all the translations in all the three directions. Okay, so we can see here the supports. Okay. So now we can continue by defining the properties for the different materials of the house. So we can start with the concrete for the foundation, that we will use a linear elastic isotropic material. So we select the shape property assignment and we select the foundation, and we will use regular curved shell elements, and we need a new material. We'll call it concrete, or concrete can be concrete. Concrete, and it is a linear elastic isotropic. We put here the parameters for elasticity. Okay. We add a new geometry that we will call foundation 2, with the thickness of the foundation 0.5 meters. Okay. And it's everything for the foundation. Okay. So now we define the masonry of the walls by using the new engineering masonry model. And for that, we will need to define two geometry types, because we need to define a local x-axis in the direction of the bed joint, and then one material model that will be the same for all the walls. So we start by defining the new material model. So here in the geometry browser we can go to materials. We already have the ones that we defined previously, and we add a new material that we will call masonry concrete, and we will use the engineering masonry model. Okay. So now we add first the elasticity parameters in the two directions. Now the cracking parameters, we will choose the head joint failure type, the diagonal staircase cracks. Fracture energy and the angle. Okay, we continue with the crushing parameters. Okay, and the shear failure parameters. Okay, and crack bandwidth is the default. Okay, we have everything. So now we define the two element geometries. The thickness is the same, and the definition of the local x-axis differs. So we go here to the element geometries. We already have the one for the foundation. So we add a new element geometry that we will call walls in X direction, is for a sheet, and is regular curved shell elements. Okay. Okay. So the thickness 0.1, and in this case we are referring to the walls in the X direction, which is this one and this one. So the bed joints will be in the direction of the X global axis. So in this case the element X-axis is corresponding to the global X-axis. Okay. And we need to define in the walls in Y direction. We can duplicate this one and rename it as walls in Y direction, and we can edit this geometry. And now we are talking about this walls in the y direction. And in this case, the bed joint direction is aligned with the y global axis. Okay. So now we have the geometries and the materials, and we can assign it to the walls. So we go to the shape property assignment, and we select the walls we start with the walls in the x direction. And we choose the element class is regular curved shells. The material is masonry, and the geometry is the walls in x direction. Okay. We do the same for the walls in the y direction. So shape property assignments, we select the walls in the y direction. And it is regular curved shells, material masonry, and now geometry is the walls in the y direction. Okay. So we continue the material and geometry definition with the roof. So for the beams of the roof, we'll use a linear elastic isotropic material model, and class 2 beams 3D with a rectangular cross-section. So we select the shape property assignments. I'll have this selected. Okay. I can go here to the geometry and select all the beams. And so we will use class 2 beams 3D, and the material, we need a new material. We can call it roof beams. Linear elastic isotropic. Okay. We now give the properties. Okay. And we also need a new geometry. We call it roof beam. It's a rectangle, and we define the cross section 0.2 height and 0.05 width, and we define the local element z axis, which will be minus y. Okay, we have everything. Okay. So now we define the properties of the roof plate. So we select the roof plate. It is regular curved shells. We need a new material. We'll call it roof plate. And linear elastic orthotropic. Okay. So here in the element type we have the curved shells, and we define the material properties. Okay, we have everything. Okay, so we continue with the geometry. So we call it roof plate, and we give the thickness. Okay. Okay, so now all our geometry and properties are assigned, and we continue by setting the loads. We start with the self-weight, so we attach a global load, which we'll call self-weight, load case self-weight, dead weight. Okay. And we now define the pushover load. So attach load, we will call it pushover, new load case called pushover. Target type is solid, and we choose the model pushover. Now we select all the shapes, and now the directions, so we want to apply it in all directions. Here's the acceleration of gravity, 0.8. And here we define the eigenmode to be considered. We will, in this case, we will assume is mode shape 1. We have to confirm this with the eigenvalue analysis. We will see that afterwards. But for now, we assume that the sway mode, the dominant mode for the pushover, is number 1. Okay. So now we define the mesh. The mesh seedings first. So we select all the shapes, and we set an element size of 0.3. And we can preview the mesh. Oh, it is okay, okay. And we generate the mesh. Okay, so we have a nice mesh, and we can move on for the analysis. So we go to the analysis browser, and we add an analysis. And the first thing we do is an eigenvalue analysis to check the dominant modes. So we add a structural eigenvalue, and we want to ask for the 5 eigenfrequencies to be computed. Okay, so we run this analysis. You can see here in the message box that we have the 5 eigenvalues. And now we can check the results and see the displacements. So here are the total displacements. We can see here the original shape. And this is mode 1. Mode 1. So this is mode 2, mode 3, mode 4, and mode 5. So we confirm that mode 1 is the sway mode that will be dominant for the pushover. So with this, we can continue with the pushover analysis. So we'll need to make a structural nonlinear analysis until failure. So we add to analysis number 1, we add structural nonlinear. So we need to execute blocks, one for the self-weight and the other for the pushover load that we will increment until failure. So we add a new execute steps with load steps. So we can rename this execute blocks. This is self-weight first, and then we will do the pushover. Okay. So in the self-weight, we do load steps with the load set self-weight, and we can put it in 2 times. Okay. And we keep all the equilibrium iteration settings as default. And for the pushover, the load set is the pushover. And as we are doing nonlinear analysis until failure, we will need to increment this pushover load until failure. So we'll give 0.5 of step until a large number of steps that we don't know until it's failure. Okay. And we will also need to activate the arc length that will give us control to follow the path of response until failure with automatic scale of load steps. So we activate the arc length and the settings. So we use the regular, and we need to define a new set of nodes to be controlled by the arc length. Okay. So I want to control all the nodes except ones that are restricted. So I come here to the mesh, and I don't want to see the interface because there are supports in the interface. So I want to select all the nodes except the ones from the interface. Okay, we have all the nodes selected, and I want to follow the X direction. I can see here the referential. That is the main direction of the loading. Okay. So we have the arc length defined. Okay. Another thing, also we need the nonlinear effect. In this pushover analysis, the geometric nonlinear effects will be important, so we have to consider it. Okay. For the equilibrium iteration, as we are doing this analysis until failure, we need to define some extra settings. So we increase the maximum number of iterations to 50. We use the secant quasi-Newton method, and we follow the displacement convergence norm. We also set the non-convergence to continue. Okay. So I think with this, we have our analysis completed. We now want to define the output. So for the output, I want to ask for results each 5 load steps. So I ask from 5 to 100 in each 5, an interval of 5. And for I use the user selection for choosing the results I want. So I want displacement. I want strains. Also crack widths and principal directions. I want stresses, Cauchy stresses, and also reaction forces. Reaction forces. Okay, we have everything. Okay, with this we have all the analysis defined, and we can run the analysis. We run the analysis. So as this will take a while, I already have here the computation made to show you the results. So first there are the eigenvalues that we already saw, and then we can see the results of displacements first. So we can see the displacements. We can see the increment of displacements here in the legend following this first mode shape. And then in load step 23 we have failure, collapse, and DYANA retrieves load step 22. So this is because of the near collapse output tool that we didn't ask for load step 22, but as it is immediately before divergency, we get this result. So we can also see crack widths. We can see crack widths in principal direction. We can ask for the maximum of the layers, and we can see its increment. And the concentration, here is collapse, and we can see the concentration of damage near the door gap. Okay, so we can see the damage, but we can also do the pushover curve, the displacement versus the total base shear force, and for that we want to select one node, and in the displacements we want displacements in the X direction, so we ask for the table, and we want for all the cases, so we can copy paste this data to Excel, and here it is, an Excel sheet. Okay, all the results. And to make the graph, I want the reactions also. So I want the reactions in all the supported nodes. So I ask for the reactions in the X direction, so table, and I can also copy this data to Excel. So to have the total base shear force, I need to sum all the reactions for each load step. I already have that made, so we can see the graph, the pushover graph. So this is displacements in the X direction versus the base shear force in the X direction. So we see here the pushover curve with the capacity of the house, and this is the last step before divergency, before the collapse. Okay, so now we made this pushover analysis for the mode shape number 1, but we can still have doubts if it's really the dominant shape mode. So we can go back to these results of the mode shapes. Let's see again this displacements. So we see this is mode 1, that is loading the walls in the Y direction. Mode 2 is about the roof, and mode 3 is about the walls in the X direction. Mode 4 is already a mix of modes, and mode 5 too. So let's choose mode 3 and make a pushover analysis considering the shape of mode 3. So we can go back to geometry, and in the geometry browser, in the loads, we have here the pushover load, and it's defined the eigenmode to be considered number 1. So we can change this to number 3. And we need to remesh because this was assigned to geometry, and we can run the analysis again. As this will take a while again, I have here the computation and the results of this pushover for the mode 3, and we can take a look to the displacement, global displacement, with the increment of load now in the direction of the mode 3, and this continues until a while. You can see the last one, and we can also see the crack widths now for this pushover shape. So crack widths, and also for the maximum, and we can see the increment of cracks, and also now they locate in a different area. Okay, so now to be sure that the mode shape 1 is the dominant one, we want to make another pushover curve for mode shape 3. So we select a node in the wall, in this wall, and we do the same. We ask for the displacements now in the Y direction in the table for all the cases, and we do the same. We put it in our Excel sheet in another one. We use another one. Okay, and we do the same for the reactions, but now the reactions in the Y direction for all the cases. And to have the total base shear force, we would have to sum them again. I have here the graphs for the pushover eigenmode 3. So the blue one is the eigenmode 3, and the green one is the pushover for eigenmode 1. So we see that the eigenmode 1 is the dominant one. So we confirm that. So now what I want to show you is some brief insight into nonlinear time history analysis of this same house, of this same model. So I have here prepared our same model. So we need to input in the loads the acceleration spectrums in all the 3 directions for our earthquake. So we see here in the X direction, in the Y direction, and in the theta direction for 3 seconds. We also need to define the Rayleigh damping parameters for the properties, for the material properties, and in the analysis we now do structural nonlinear but with time steps. So we impose time steps of 0.005 seconds and we do the analysis. This will take a while. So I show you the results I got. So here for the time steps, we can see the total displacements. So now we can see the total displacements for each time step of an earthquake acceleration. So we can, this is 600 steps, so we can scroll and increment and see the displacements, also the shapes and the deformation changes. You can see, okay, more at the end of times, okay, and we can also see for the maximum, so extreme maximum up to time step 602. Okay, so this is our maximum. We can see also the development of cracks under this earthquake excitation. So we want to see the crack widths. See the crack widths, and we can see the increment of the crack widths, and also we can set the maximum of 5 layers. We can see how they change the location with the time, with the different excitations. Can go a little bit further in time, okay, a little bit more, okay, and we can go to the maximum, the extreme, okay. So we can make some graphs of the displacements in the x and y direction with time for this nonlinear time history analysis, and we get something like this. So this is the time versus the base shear force, and the time versus the displacement in the x direction, and the same for the y direction. As we saw that the pushover mode shape 1 was the most critical, we will compare the extreme results of this nonlinear time history in the x direction with the pushover of mode shape 1. So here we have, this is our pushover curve, and here these dots are this one is for the maximum of the full nonlinear time history analysis, and this one is for the minimum. And here we have the counter plot and the deformation of the for the corresponding time. We can see here that this is the drift of the displacement. So in DYANA you can output the drift, which is the displacement in relation to a reference that you can set. In this case, our reference for the drift is the base. And well, if you see these results, you can see that the pushover analysis is conservative, so we don't have damping, we don't have the correlation between the modes. Even though we can make a parallel discussion about these results. So here in the left, we have the extreme maximum, the displacements in the x direction for the full nonlinear time history analysis. And on the right, we have the pushover for the maximum in the collapse. So we see a similar dominant response. And also, if we look to the cracks, and here in the left for the nonlinear time history, the maximum, and on the right the pushover, we can see cracks located at the same areas near the door gap. However, the pushover presents it's conservative. It gives larger numbers of the crack widths in comparison to the nonlinear time history. Okay, so with this I finish this webinar. I want to thank you for attending and thank you for your attention. So please send us your questions now or later by email, and we will try to answer. Well, this analysis is also presented in a tutorial that is available in our website, and also keep a look on our website for more webinars and tutorials. So thank you.